No one has joined so far. अभी तक हाँ
8 लोग हैं सर, देख रहे हैं।
हाँ 8 लोग हैं. Okay. Hello everyone. Good afternoon. Can you hear me? Of course, you cannot speak, but you can write. Okay. Can you hear me? उनका नाम देख सकता हूँ मैं. Honey, you have any questions? How is it going, the course? Oh, nice. So you took my main group chemistry course also? Hi, Sagar. You have any query? So how is it going? Hello, Dr. Smita. So another 2 weeks are left, right? So another 2 weeks are left. So that means another 10 lectures are left, right? You have any difficulty in understanding or you need some clarity? Yeah, good evening to all of you. So you had any problem why you couldn't write assignments or attend all the assignments, Dr. Smita? Probably time, right? Yeah, you must be busy teaching also, right? Yes, okay. That's an interesting question. You should know the difference between qualitative and quantitative terms. Qualitative means, telling about uh, the type of chemicals or something involved in it. Okay, where quantitative gives how much quantity it is there. See, for example, when we do titration, it is quantitative. Okay, we are determining the actual amount of chemical present in a particular system while doing analysis. Okay, if we, for example, when you do acid and base radical identification, that is qualitative. We only tell in a particular chemical what are the components present. For example, if you take sodium chloride, we analyze and we say sodium ions and chloride ions are there. That is called qualitative. Okay, and if you do estimation and to tell in a given sample how much quantity of a particular salt or a compound is there, that is quantitative. Okay, is that clear now? Oh, nice to hear that course is going good, Sagar. how to find the equivalent mass for organic molecule annealing. That you should be able to tell. What is the meaning of equivalent mass? And how to find out molar ratio? Okay, see, if a compound is given in grams and molecular weight is known, you should be able to tell the given amount is equivalent to how many moles. Okay, in the same way, you can also calculate that. So there was a question about the nature of organometallic compounds involving main group elements and transition elements, right? So all organometallic compounds can be classified into two types. One is organometallic compounds of main group elements that I discussed, okay, in my main group chemistry. So of course here I didn't elaborate organometallic chemistry in this course because it is more devoted towards coordination chemistry and okay, other things. If you want to know the difference between organometallic compounds of main group elements and transition elements, one thing you should remember, okay, so we are making metal to carbon bond. Okay, we have main group metals also. Main group metals mostly come from alkali metals and alkali earth metals, S block, and also quite a few in the P block. Okay, so we are talking about making main group elements to carbon bond. But one thing you should remember, if you look into energy associated with an organic compound having a carbon to main group element bond and also another transition element organometallic compound having carbon to a transition metal bond, the energy associated is more or less similar. The energy associated with those bonds are more or less similar. Then why some organometallic compounds are unstable and some organometallic compounds are stable? So for example, if you cannot really compare the organometallic chemistry of S block elements with transition elements compared to transition elements. Okay, in case of S block, organometallic compounds are less stable because carbon is more electronegative compared to alkali metals. As a result, carbon carries more negative charge. When it carries more negative charge and the bonds are more or less highly polarized, okay, in that case, they are highly reactive and susceptible for hydrolysis. But on the other hand, main group elements, if you just look into it, main group, the electronegativity difference between oxygen and carbon, nitrogen and carbon are very minimum. As a result, they have more covalent character and hence they are more stable. In case of transition metals, what happens? Transition metals can always expand their coordination number. And due to this one, what happens if there is a substance such as water comes in close vicinity of organometallic compound, it can establish a bond through vacant site and then it can attack. This is hydrolysis. On the other hand, even if it doesn't have a unsaturated coordination sphere, unsaturated or it doesn't have a vacant site, okay, so some of the metal to carbon bonds can decompose or they can extend its coordination number by shrinking their coordination sphere. So this is where beta hydrogen elimination comes into picture. If you have beta hydrogen that can form conveniently a four-membered ring that I have shown, okay, once that is done, what happens? The alkene comes out and metal to hydrogen bond is formed. Again, metal to hydrogen bonds are also in many cases unstable. So that leads to the decomposition, and if moisture is there, eventually you can see the formation of metal oxide. Okay, so this kind of reactivity is restricted in case of P block elements. Okay, when you have like phosphorus to carbon bond, there most of them are tetra coordinated or having 4 coordination, and there is no scope for expansion. So kinetically they are all inert. Whereas in this case they are kinetically not inert, active. So that's the main difference between organometallic compounds of main group elements and torsion elements. When you go to alkali metals, because of huge electronegativity, carbon ions, okay, are more, okay, they have more, or the carbon ion character is more. As a result, those compounds are unstable. Okay, the moment they look for, okay, uh, a, a molecule where, okay, carbon ion can get rid of its, okay, excess electron and to form some covalent bond, it goes for that. So that is the reason we use some of these alkali metal and alkaline earth metal compounds in the form in carbon-carbon bond formation and other things. Okay. So you said we didn't discuss the functionality in organometallic. Well, of course, as I mentioned, this is not a fully organometallic chemistry dedicated course. That's the reason I didn't give much emphasis for reactivity of organometallic compounds. Nevertheless, by keeping certain aspects of coordination chemistry only, I discussed it. Okay, so in a more dedicated organometallic chemistry course, probably will come across. Maybe in future, I may float another course fully dedicated to organometallic compounds. In that, I shall discuss some of these things that you have in your mind. So for inorganic reaction mechanism, D.F. Shriver's book is good, and there is one old book is there that is by Basel and Pearson. Okay, that's the old edition. It was 1960s edition, and we don't have any. There is one more book called G. Wilkins' Inorganic Reaction Mechanism. So that book is also good, but most of the aspects, whatever I'm discussing, can be found in D.F. Shriver's Inorganic Chemistry book and also Housecraft Inorganic Chemistry book. Okay, so Nabil is asking a question. My question is how we got the energy level diagram of complexes as we don't have either symmetry interaction dominance or energy gap dominance for overlapping. Okay, so when we write about multi, or polyatomic molecules, I already mentioned you have to segregate into two groups. For example, MCO6, when we are writing, M is one entity and remaining 6 carbonyl groups are another entity. So here we are considering ligand group orbitals, and that comes from the linear combination of symmetry adapted linear combination of atomic orbitals. Okay, so that physical chemistry people discuss in length. Okay, symmetry adopted linear combination of atomic orbitals. From there, we consider ligand group orbital as one set of atomic orbital and the metal another one, and depending upon their energy, we are keeping them, okay, up or down. Most of the time, the ligands will be having little lower energy compared to the atomic orbitals of metal, and then you will start putting interaction, you start showing interactions with appropriate orbitals from both the entities. So this is how we write. You can look into YAMO diagrams I have generated for many complexes. Okay, all kind of complexes I have given YAMO diagrams where we have pure sigma donors, we have pure sigma donor and pi donors, and also sigma donor and pi acceptors. Please look into it. Okay, if you still you have doubt, you can always come back to me. Oh. Well, if you go for heavier elements where we have D8, D9, D10, S2 electronic configuration, if they adopt 6 coordination, obviously they will be violating 18 electron rule because you will be having in excess. For example, if you take zinc, we have 10 electrons are there. And if you form a hexa-coordinated compound, obviously you will be having more electrons. Okay, so that's the reason we call this outer orbital complex comes into picture, and many outer orbital complex do have in excess of 18 electrons. That's quite true, and many of them are moderately stable as well. Okay. Okay, if you replace ethylene moiety with cod, yes. You see, cod we have, okay, two double bonds, okay, whereas it's almost like taking ethylene, two single bonds are there, and there is some element of chelation is also there that stabilizes, but there may not be much significant difference in the bond lengths between ethylene as well as cyclooctadiene. Okay, that difference may be very minute. Well, I have examples. I shall look into it, and maybe I can tell you. Okay, a precise. I have examples in our laboratory research where we have ethylene as well as cyclooctadiene bound metal species. Let me look into it. How much difference will be there? You cannot make it because it also depends on other ligands present on the metal, and also relative trans effects will also come into picture. But nevertheless, okay, the card, there is one thing, card forms a chelate compound. There's one thing. On the other hand, card is also highly strained. That's the reason reactivity comes in it. For example, if you take that one and if you treat with some other 2-triphenyl phosphine or something, it can readily come out because little bit of strain is also there. And if you go for another one, nalbornadiene, okay, or it is called heptadiene, okay, bicycloheptadiene. So if you compare bicycloheptadiene and cyclooctadiene, cyclooctadiene less strained compared to nalbornadiene, so nalbornadiene can readily come out. Yeah, zinc. Okay, yes, obviously, the moment you look into trisethylene diamine zinc, okay, so zinc is in 2+ state, so you have 10 electrons are there, and 10 electrons, and each ethylene diamine is giving 4 electrons, right? So 4 into 12, okay, so 22 electron species. Yeah, it is exceptional. Stability also comes from chelate ring formation also, okay, so what happens? The entropy increases during the formation of tris ethylene diamine zinc compound. That also adds to its stability. Well, notes is not necessary. So what happens? You listen to the lectures carefully and then go to the textbooks, okay, and refer textbooks. Then that is more helpful than me providing a PDF to you. If I give a PDF of the lectures, you may not look into textbooks at all, right? So that can do more harm to you. On the other hand, whenever you listen to my lecture and to expand the topic, whatever I am discussing in a particular lecture, okay, go to relevant textbook and make your own notes, okay, so that you will not forget and there's no need for you to read again. Well, organometallic chemistry or coordination chemistry, plenty of books are there. Why do you want notes again, right? Why do you want notes again? Okay, readily available textbooks are there. You can look into it. If you ask me to tell important topics in advanced transmetal chemistry, whatever I had discussed, it is very important. And for what important is what matters. Okay, if you want to learn the subject or if you want to write examination. If you want to write examination, you should look into the syllabus and see what kind of questions are coming. Okay, I'm not the right person to answer about those things. But if you want to know about understanding the subject, yes, everything, whatever is discussed in this course is very important, but you should remember to expand it by going to textbooks. After all, I have only 30 minutes in a lecture, okay, not more than that. Well, individual compounds are stable, okay, so then again, for example, label studies, we look into it, okay. When we look into label studies, exchange of radioisotopes, for example, cyanide, okay, hexacyano, ferrate, if you take and treat that one with labeled one, it exchanges, okay. If it is exchanges means what it says is it's about kinetic stability versus inertness, that is it. Okay, if you say compound is stable, it doesn't mean that it's not reactive or something. Okay, so it depends upon the type of compounds we have. Yeah, about this only, just look into G. Wilkins' book. He describes all those things very nicely. Well, I don't have book right now, so that's the reason. If you had question in advance, I would have looked into it. So I cannot open a book to explain you now. Whatever is there about a palladium compound in page number 545 or something. So always you should give that questions whatever you have in at least in one day advance, because everyone, I cannot start looking into the book and assay the problem. Okay, best would be to pose the question well in advance, okay, and then probably I can come up with satisfactory explanation to you people. If everyone asks me to go to that page or this page in a particular book, okay, in a discussion like this, it's not possible. Okay, next live session I am taking after a week or so. You have enough time, keep your questions ready. Okay, whatever the book you are referring, you keep the questions ready, and also write fully the question in advance, because here it takes a lot of time for you to explain it, and if the molecular formula or something has to be written, it's difficult. So keep everything ready and post it to me. Okay, I can give you satisfactory explanation to your doubts. Okay, your CP, rhenium, carbon monoxide, PF3, xenon, it is 18 valence or not. Okay, so that you should be able to do it yourself. Okay, you are writing xenon. Xenon, or it's a halide, some halogen. Isopropyl CP, one of the CH bond, H is replaced with isopropyl. Is it C5H4 isopropyl? So let's consider there is no difference between CP star CP and you have substituents, because all are okay 6 electron donors. That goes up. Huh? Yeah, this is your question, right? PF3. I cannot read the question now. The question is, can you see?
Yes, sir. Iridium, CP, neon,
Huh.
xenon.
Xenon. Xenon is xenon?
Yeah.
What is xenon here? Is it X? Is it you are referring this one to some halogen, Cl, bromo or iodo? Just let me know. Xenon is not a ligand. Of course, in principle it can be a ligand. It has 8 electrons in its valence shell. It can be a tetradentate ligand. Unfortunately, it's not very easy to use it as a Lewis base. Okay. Of course, rhenium, if you consider, rhenium has D5S2 electronic configuration, right? So we have 7 electrons are there. Let's go by neutral method. Let's assume this one as a halide. Okay. So if you go with this method, rhenium has 7. This is by neutral method. Neutral method, we are taking all the electrons present in the valence shell of a metal. So 7 plus CO gives 2 electrons. PF3 is a neutral ligand. Okay. Is there eraser? Oh, it goes. Press. You have to press it. Oh, okay. 7 plus carbon monoxide is giving 2 plus PF3 is giving 2 plus Cl is giving 1. Okay, so now plus this one is giving 5 electrons. So how much it is? 17 electron species. Right? This is 17 electron species now. Okay, so but on the other hand, if we know this is X, so and these two are anionic ligands, so then it will be 5 plus Cp will be 6 plus CO will be 2 plus 2 and plus this will be 2. This is 17 electrons. So this is a 17 electron species. Okay, this one is not 18 electron. It is a 17 electron species. Is that clear? But if you consider xenon, it is acting as a 2 electron donor. It's a neutral. Then it can be. I mean, in case if you are considering this as a xenon, not halides, then what would happen is its oxidation state will be +1. So in this case, what happens? 6 plus this is 6 plus 2 plus 2 plus 2. Okay, this is 18. Okay, this is correct. So then rhenium will be in +1 oxidation state. Xenon will be, let's assume xenon will be 2 electron donor. Then it becomes 80 electron species. Okay, if it is X, halogen, halide, like chloride, bromide or iodide, then rhenium will be in +1 oxidation state. Okay, +2 oxidation state, and it will be 70 electron species. But here rhenium is, if you consider xenon, yes, I can give you answer. Cp is 5 electron donor in neutral count method, whereas in ionic method it is a 6 electron donor. So 6 and rhenium is in +1 state, so you have 6 electrons are there, and carbon monoxide, trifluorophosphine and xenon are giving 2 electron each, so it is 8 electron species. Is that correct? Can see the more discussion. Okay, if it is xenon, good. If it is xenon, it's the 80 electron species I showed you here. Okay, this is correct. Okay, so right, so this is correct here. So in this case, so this also 6 electron, so it becomes 18 electron species. So here xenon is a 2 electron donor here. Okay, this is a 2 electron donor, 2 electron donor, 2 electron donor. This is 6 electron donor, and here oxidation state is +1. Okay, so we know now 6 plus 6 plus 2 plus 2 plus 2. So 18 electron. Right? Is that clear? Yeah. Well, in case if such elements are given like xenon, krypton or something, obviously you should consider them as 2-electron donor. Okay, it cannot be 4-electron donor. Okay, it can be 2-electron donor. And if two metals are there, and if they speculate something, and if they say xenon is a 4-electron donor, then it can be a bridging ligand. In that case, there should be two metal moieties should be there. Sometimes such questions might come in some competitive exams. How to find, okay, yeah, it is, see, for example, carbon monoxide, whether it's acting as a terminal ligand or a bridging ligand, it's always 2-electron donor. Okay, it's always a 2-electron donor. And if it is bridging, then what happens? We have to see whether the metal is coordinatively saturated or not. If the metal is not coordinatively saturated, then whatever the ligands are there, they should try to, okay, compensate the lack of ligands. As a result, what happens? Carbon monoxide, sometimes it can bridge 2 or 3, even 4 metal centers. In that case, what happens? No matter how many contact it makes with metals, it's always 2-electron donor. Okay, do you remember? We wrote something like this. These are the electrons, they are responsible for carbon monoxide to act as a sigma donor. And if we consider two metals, so we write like this. Of course, whether it's bridging or not, you can make out by simply looking into IR stretching frequency. If it is terminal, IR stretching frequency will be having higher value. Okay, if it is bridging, what happens depending upon how much electron density is coming from metal to pi star of CO, antibonding of CO, it can become ketonic carbon. In that case, drastically CO stretching frequency reduces and it can be compared with ketone in organic compounds. So you should be able to just tell simply by looking into IR stretching frequency. And first of all, there should be two metals in order to make carbon monoxide, okay, behave as a bridging ligand. Is that right? In the absence of all those, simply you should look. For example, let me next page. Okay, so let me give you this example: Cp, Fe, CO2 dimer. Okay, so if you see here, 4 carbon monoxides are there and one Cp group, 2 Cp groups are there. So that is not enough for giving coordinative saturation to metal. I know the structure, I will write you the structure that will give you some information about the nature. So this is how one can write. So one you write here, one you write here. So other one will be bridging. See one thing, so something like that you should try to work out. One is here, of course, IR spectrum of this compound can tell you presence of two type of carbon monoxide, one bridging and one terminal. Okay, that simply by looking at stretching frequency. Other one is any given molecule would always try to have a highly symmetric structure. Okay, in that case, you see, and that means you can see now it also has a center of symmetry. On the other hand, and it also 17 electron species, you need one bond, metal-metal bond. In order to stabilize metal-metal bond, you need two anchoring ligands also. Okay, these anchoring ligands will bring two metals to establish a stronger covalent bond so that the molecule is more stable. So in this case, what happens, two of the carbon monoxide will bridge here. And of course, when it's bridging, you should remember it is a 3-centered 2-electron bond only. You should remember that one. Okay. Is that clear? There are several ways to assess the nature of CO. One is it can be terminal. On the other hand, it can be bridging provided more than one metal center is there. And again, writing the structure, you should give importance to the symmetric structure. Okay, automatically you will end up with writing the correct structure for that one or identifying if choices are there. Coordinative unsaturation means, for example, you take palladium. Palladium normally can have 4 coordination or 6 coordination. When palladium is in +2 state, nickel, palladium, and platinum in +2 state, so they prefer to have 4 coordination, and the preferred geometry is square planar. Okay, and in case if bulky ligands, if you stabilize palladium with 3 coordination number, then they are coordinatively unsaturated, we call, because it can accommodate one more because of the bulky groups are there. So that means this is called coordinative unsaturation. And if a transition metal, especially 3D ones, they can have up to 6 coordination. Okay, and if 6 coordination is there, 7th cannot come, we say it is coordinatively saturated. Oh, well, you cannot really tell about, see, 18 electron complexes, you should remember, 18 electron complexes, when you are doing substitution, of course, substitution can follow SN1 mechanism and SN2 mechanism. If you consider associative mechanism, what happens, it has to accommodate one more ligand at least. So when more ligand is coming, and if there is no change in the oxidation state, if the neutral ligand is coming, there will be addition of 2 more electrons. If it is already saturated with 8 electron, it has less tendency to go for 20 electron species formation as an intermediate. As a result, preferred mechanism would be dissociative. But in some cases, yes, in some cases what happens, the arrangement can be changed, because NO, if you take NO, can be 3 electron donor or it can be 1 electron donor. And similarly, CP can be even 2 electron donor or even 3 electron donor, or it can be 5 electron donor. So this kind of flexibility is there in the donor properties of ligands. Wherever such flexibility is there in the donor properties of ligands, okay, you can also anticipate associative pathway. For example, if associative pathway another ligand is coming, so NO, let us say NO has a linear structure with 3 electron donor property, it can have a bent mode and it can become 1 electron donor. So in that case, what happens? 2 electrons still you need if it is saturated one. In that case, the incoming ligand can come, and there is enough space for that one, provided enough space is there, provided it's coordinatively unsaturated. So this is how, okay, even associative pathway can also be explained in case of molecules or complexes having NO as well as CP ligands. Is that clear? After ATMC, which course will come? Okay, that is suspense. Okay, keep waiting. Okay, and also if you have something in mind, tell me. Okay, if you want me to take another course on some topics of your interest, let me know, honey. This is suspense. Okay. You are particularly interested in any topic that I should come up with? So what you are studying, honey? Oh, coordination chemistry is already there in this one, right? I have discussed the coordination chemistry in more or less in depth, even giving the historical background, okay, all those things, right? So what more you expect under coordination chemistry that I missed? So any other questions from others? Sagar? Okay, good. Okay, so study these textbooks as I mentioned, and also look into my both the courses, and I'm sure you should be able to do well in your exams. Oh, inorganic spectroscopy. Okay, that's interesting. At the end of this topic, I tried, but lack of time, I couldn't elaborate. I have to rush it. Okay, yes, I do have that in mind. I want to float another course that is interpretative molecular spectroscopy, giving emphasis for inorganic spectroscopy. Again, NMR, electronic spectroscopy already I discussed briefly, giving some insight into Thunbe-Sugano diagram and what is the other one? Beside before Argel. So I forgot Argel diagrams. Okay, and also I made you familiar with term symbols, what is spin orbital coupling and all those things. And of course, electronic spectroscopy also one can discuss in length, and also giving more emphasis for NMR spectroscopy, multinuclear NMR spectroscopy. I shall do that one. Maybe in near future I shall take up that course and come up with lot of examples, so that you shouldn't look for textbooks to look into those examples. Certainly I will do that. It's not inorganic spectroscopy, I would say interpretative molecular spectroscopy. Okay. You have a lot of questions. You should have posted those things in advance, because it's very difficult for you to write all the questions, and you have to give some space for others also. So in this context, what you do is I'm coming again after a week or so. Keep your questions ready and post it. Okay, let me answer and clarify all your doubts. Okay, Sagar. Okay, coordination chemistry reaction mechanism. Okay, reaction mechanism I did discuss. Okay, little bit, and also I discussed about substitution reactions in octahedral complexes and square planar complexes, and more than that, I also discussed about the stereochemical consequences on substitution reactions in octahedral complexes, where considering both SN1 and SN2 mechanism. I don't think I am again going back to reaction mechanism, and also there are some courses already. I don't think I will go back again. And of course, maybe after a couple of years, what I will do is I will try to add a couple of lectures more. Probably that should help you. By the time you will be saturated with coordination chemistry, you may not read again. Okay. Okay. This exam is objective only, not subjective, but it's like multi-choice questions or something will be there, and that information should be there already on NPTEL. Okay, it's not no need to write anything. Okay, it's not subjective. Of course, we have to do a lot of calculations and other things to arrive at the answer. It's not simple ticking. My email ID is there. Okay, what you do is you just go and type MS Balakrishna on Google. Okay, it will take you to IIT Bombay website. Okay, my email ID is there. You can always write it to, right, if you have any queries. Okay. Any other questions or doubts? It takes a lot of my time, honey. Okay, so preparation, is tedious. You know that. Okay, for example, if I have to prepare 60 lectures, I have to put a lot of time. Of course, okay. If it is helpful for people like you, certainly I will do that. Okay, and maybe 23 years, certainly I will do that. Okay. So whatever the complex you come across, start writing, electron count for them and make yourself familiar. And this is very, very important. Okay, later if you go for higher studies in chemistry or you want to do PhD, and of course you cannot get away from metal complexes, especially if you are into synthesis, organic synthesis or inorganic synthesis. Complexes were very, very important, and they are been used as catalysts for organic transformations, and metal mediated organic synthesis is quite popular nowadays, not only in organic synthesis but also in pharmaceutical companies and in medicinal chemistry. Compounds can be made more readily involving few steps rather than going for multi steps. From that point of view, metal mediated catalysis, we call it as homogeneous catalysis, is very, very important for several organic transformations. Okay, so every and the 18 electron role plays in 18 electron count or 18 complexes. 18 electron system plays a major role. Okay, this counting in deciding whether a particular compound can be used as a catalyst or so. And if it is 80 electron complex, how to make it 16 or 40 electron species to begin with, or to begin with, whether I can make stable 12, 14 or 16 electron species so that I can do catalysis easily without involving further reduction. So all those things comes into picture. From that point of view, practice these things. That's very helpful. And also read more textbooks. Okay. Okay, you found some questions directly asked in GATE from assignments. Okay, that's good for you then. Okay, that's good. Then you can get good grades in it. So go through all my assignments. Certainly it helps you. Okay, and if it helps, okay, my efforts are worth. Essentially, why I'm giving all these assignments is essentially to make you familiar with chemistry, the basics, so that you can answer questions. Okay, it should not be just confined to answering questions in GATE exam. Okay, you try to understand the basics so that no matter what questions are asked, you should be able to answer without much difficulties. So if there are no more questions, okay, see you all in my next interactions. I will try to hold, depending upon how many questions are coming. I shall try to have at least another 1 or 2 sessions before this course is concluded. And as I said, all of you just note down your questions and start, keep it ready. The moment we tell you about the schedule, the next live session, post all the questions in advance, so that I can give you precise answer for those questions also. As Sagar was telling, he has a lot of questions. but he's unable to write right now. Okay, that is not my mistake. Then you should have prepared for those things. It doesn't matter. Okay, I'm giving you another couple of opportunities. Okay, keep listing all those things. No, I haven't written any book. Okay, I'm planning. Okay, I'm planning to write some books, and I have edited a book on research topics. Okay, about copper chemistry. That probably, if you take up research, then you may get an opportunity to look into that book. Otherwise, it doesn't help much for you at present. And books, I haven't. Okay, books writing takes a lot of time, and also I'm busy with teaching and research activities. As a result, I couldn't. Maybe in future I shall do that. You want me to write some books, Sagar? Okay, if no more questions, okay, thank you very much, and have an excellent time reading chemistry and digesting chemistry. So another 2 weeks to go, and then I'm sure, okay, I would come up with another interesting course for you people in near future. So I wish you all the very best. So thank you. Yeah. Okay then. Yeah. See you all.